Lens definition. A lens is formed when a transparent material is bounded by two surfaces. Here, one or both surfaces will be spherical. Types of lenses. There are 5 types in lenses. They are biconvex lens, biconcave lens, plano-convex lens, plano-concave lens, concave convex lens. Biconvex lens. Biconvex lenses are thicker at the middle. Rays of light that are passes through the lens are brought closer together. A biconvex lens is a converging lens. Biconcave lens. Biconcave lenses are thinner at the middle. Rays of light that passes through the lens are spread out. A biconcave lens is a diverging lens. Plano-convex lens. Plano-convex lenses are positive focal length elements that have one spherical surface and one flat surface. Plano-concave lens. These lenses are thicker at the edge than in the center and flat on one side. Concavo-convex lens. A lens that is concave on one surface and convex on the opposite surface are called concavo-convex lens.
Rules of image formation by spherical lenses. Number 1. In case of convex lens, if an incident ray is parallel to the principal axis, the refracted ray passes through the principal focus. In case of concave lens, if an incident ray is parallel to the principal axis, the refracted ray appears to pass through the principal focus. Number 2. In case of convex lens, if an incident ray passes through the principal focus, the refracted ray is parallel to the principal axis. In case of concave lens, if an incident ray is directed towards the principal focus, the refracted ray is parallel to the principal axis. Number 3. An incident ray passes through the optical center of a lens, suffers no deviation.
Images formed by convex lens and concave lens. The characteristics of images formed by a convex lens depend on the positions of the object. When the object is placed at infinity, the image I will appear at f, which equal to v. Image formed is real, inverted and diminished. This position used as objective lens of a telescope. When the object is placed further away from f, image will appears between f and 2f. The image is real, inverted and diminished. It is used as lens in human eye and also camera lens. When the object is placed at 2f, image will appears at 2f, as inverted. The image is the same size as the object. It is often used as photocopier. When the object is placed in between 2f and f, image will appears beyond 2f. The image formed is real, inverted and magnified. This position used as projector and objective lens of a compound microscope. When the object is placed at f, its image will appears at infinity. The image formed is virtual, upright, magnified, and on the same side as the object. This position used for eyepiece of an astronomical telescope. When the object is placed in between f and the mirror, image will appears behind the mirror and object. The image formed is virtual, upright, magnified, and on the same side as the object. It is used as magnifying glass and eyepiece of a compound microscope. The image formed by a concave lens are not dependent on the positions of the object from the optical center. The images are always virtual, upright, diminished, and also placed between the object and the lens. The following ray diagrams show the formation of virtual images for an object at two different positions.
Real-life examples of concave and convex lens. Real-life uses of concave lens. Spherical lenses are used by human beings in their life. They are used in spectacles. They are used in spectacles for the correction of a special type of eye disease called myopia or short-sightedness. These are also used in telescope for seeing the nearby objects very clearly. This is the very important use of concave lens. It magnifies the faraway object to be seen clearly by us like moon and other planets. It is also used in making binoculars, which are in turn used in military as well as for recreational purposes. These are also used in cameras. In cameras, they will be combined with convex lens to make and take beautiful pictures with great clarity. They are also used for making better flashlights, as the light from the source, here bulb, will fall on this concave lens, then it will diverge this light in many directions. This will cause the divergence of light in many directions and hence an increase in the radius or curvature in which the light falls. It is also sometimes used in cars or vehicles' front lights. These are used in laser lights. They will increase the curvature in which the light falls and will make the area in which the light falls more accurately aimed. These are also used in peepholes. Have you seen doors in which when you see through the hole, then you can see the panoramic view of the outside world or the person standing outside your door? This is due to the concave lens fitted in the hole of the door. Real-life uses of convex lenses. They are used in spectacles. They are used in spectacles for the correction of a special type of eye disease called hypermetropia or long-sightedness. Convex lens is used in microscopes and magnifying glasses to subject all the light to a specific point. Convex lens is used as a camera lens in cameras as they focus light for a clean picture. Convex lens is used as a magnifying glass.
Formula and magnification. In the previous concepts, we have learned a formula for spherical mirrors, and we also have formula for spherical lenses. This formula gives the relationship between object distance u, image distance v, and the focal length f. The lens formula is expressed as 1 by v minus 1 by u equals to 1 by f. Equation 8. The lens formula given above is general. It is valid for any spherical lens wherever the object may be situated. Magnification. The magnification produced by a lens, similar to that for spherical mirrors, is defined as a ratio of the height of the image and the height of the object. It is represented by the letter m. If h is the height of the object and h dash the height of the image given by a lens, then the magnification produced by the lens is given by m equals to height of the image by height of the object equals to h dash by h. Equation 9. Magnification produced by a lens is also related to the object distance u and the image distance v. This relationship is given by magnification n equals to h dash by h equals to v by u. Equation 10.
Now we've been studying properties of images formed by the spherical lenses. Take a moment and go through the properties. One of the properties of an image is its position in space. From these tables, we see that the position of the image changes as the object's position changes. There is an equation or formula which gives us the relation between the objects and the image's position. And that formula is what we call the length equation. Let me just write down this equation first. This is the length equation. 1 over f is equal to 1 over v minus 1 over u. In this equation, there are three unknown quantities. U represents the object's distance from the lens, v represents image distance from the lens, and f is the focal length. To understand this, let's consider a case for a convex lens where object is kept beyond 2f1. What will be f here? It is the distance between the optical center O and the principal focus of the lens. This distance will be equal to f. And this distance will be u and this will be v. This length equation is valid for all spherical lenses as well as for any position of the object. However, we can't use this equation directly. There are some sign conventions that we must follow before using it. And what are those conventions? We follow the Cartesian sign conventions. Do you remember the Cartesian sign conventions we'd seen for spherical mirrors? Here they are. The object is always placed to the left of the mirror. Distances are always measured from the pole. Distances to the right are positive and to the left are negative. And distances above the principal axis are positive and below it are negative. The concept is similar for lenses. For our lens, we assume the optical center to be the origin. So the first convention we follow is that we always keep our object to the left of the origin or the optical center. Can you guess the second convention? Second convention that we follow is that we measure all the distances from the optical center. For instance, if we take this point on an object, then the distance of this point from the lens is measured from the optical center of the lens like this. The third and the fourth conventions are easy. Here they are. I'm sure they're self-explanatory. What is that we measure above and below the principal axis? Yes, the heights of the object and the image. And what do we measure to the right and the left of the optical center? Yes, the positions of the object and the image. But according to the first sign convention, the object is always kept to the left of the optical center. This means that the object's distance from the lens will always be negative. But the image distance could be positive or negative depending on its position. What about the focal length? Well, the focal length can be measured on both sides of the lens, right? Isn't it the same on both the sides? Which is why there is a fifth rule that tells us the sign convention for the focal length of a lens. For a convex lens, focal length is considered to be positive and it's considered to be negative for a concave lens. So these were the 5 sign conventions that are used for the length equation. In the next video, we will see some examples based on this equation. See you there.
Topic is lens maker's formula. What is lens maker's formula? Let us understand in detail. This is a convex lens. Material of the lens is having refractive index NB and the surrounding medium has refractive index NA. The first refracting surface of the lens, the sphere of the first refracting surface, center of curvature of the first refracting surface, radius of curvature of the first refracting surface. This is second refracting surface, the sphere of the second refracting surface, center of curvature of the second refracting surface, and this one radius of curvature of the second refracting surface. This line passing through C1 and C2 is the principal axis. When a beam of parallel rays passes through the lens, they are converged to a point. It is called as focus, and the distance from lens to the focus is called focal length. The equation representing the relation between refractive index of
the surrounding medium, refractive index of the material of the lens, radii of curvature of the lens, and the focal length of the lens. The relation between these 5 terms is called the lens maker's formula. It is 1 by f equal to nb by na minus 1 into 1 by r1 minus 1 by.
Power of a lens. Power of lens is the reciprocal of its focal length in meters. It is represented by the letter P. The power P of a lens of focal length f is given by P equals to 1 by f of m, or f equals to 1 by P. The SI unit of power is diopter D. When f equals to 1, m, P equals to 1 by f equals to 1 by 1 equals to 1 diopter. 1 diopter is the power of a lens whose focal length is 1 meter. The power of a convex lens is positive, and the power of a concave lens is negative.
For inspiration, The Art and Science of Asking Question is the Source of All Knowledge by Thomas Berger.